Hello everyone, good afternoon, and we are again in the live session. This is our second live session. So before we start discussing some of the queries that you've raised, let me quickly check how many of you are here. So I will suggest one by one, if you can switch on your camera and please introduce yourself. So first person, Injamamul Haq. Are you there? Injamam? Next person, is Das. Oh. Oh. So if nobody is there, then switch off the session. Again. Yeah. So, hello everyone. Good afternoon again. We are back in our second live session in this course, and we are about to start our discussion. This time, what I plan is we'll quickly brush up what we have covered, and then as we go through the course, then also some of the questions are there. So we'll take up those questions. Before that, let me check over here. Shishir is there, right? Yeah.
Yes, sir.
Can you hear me, Shishir?
Yes, sir.
Okay, very good. Very good. Okay, so let me first quickly go through the entire course and then some of the key points that we discussed, because this course is dedicated for MTech students. So those particularly who wish to take it for their master's project, this typical issues of reliability analysis will be of interest to them. So that for that reason only, let us first quickly go through the topics, and then I will take the questions. I believe all of you can see it, right? Please confirm.
Yes, sir.
Shishir, can you see it?
Yes, yes, sir. I am able to see. Yes, sir.
Can you see the slides, Shishir? Please confirm.
No, no, sir. No, sir. Not slide. Where one seeing you.
Can you all see the slides?
Yes, sir. Now we can see slides.
I can't hear you, Sushil.
Yes,
Please
sir, we
unmute
can.
yourself and then speak.
Thank you.
Can you see the slides, Sushil?
Yes, sir. Yes, sir. Yes, sir.
Okay. Okay. So let us start our discussion. As I told you earlier, that this course is dedicated for master's students. So the main theme is when we do structural design, particularly we consider different deterministic parameter, but in reality, when we end up with the practical problem, some of the parameters are not deterministic. And that's the reason we need to incorporate uncertainty in our design. But identifying the problem is one thing, then formulating the problem is the next step, and that's the main theme of this course. So basically, we bridge the gap, the deterministic design on one side, and the uncertainty quantification on other side. Now, when we bridge these gap and we get the design which is based on the theory of probability, and that's where we end up with the reliability-based design. So this was basically the entire syllabus, because in this course, it primarily deals with uncertainty and its quantification. Obviously, we have to use the theory of probability, and that's the starting point. So a significant part of our discussion actually is aimed towards that development. So we defined random variables. Again, in this case, we only need random variables at the end. When we have introduced you to stochastic FM, you have seen that their random field is also used. Nevertheless, in this entire course, we use the concept of random variables, and then we define the algebra of variance, and then also the joint and conditional probabilities, right? And then once we do that, we then first define the concept of reliability. So that is the starting point. And it gives you a clear idea of how the deterministic design based on factor of safety is modified, and then we bring in uncertainty and define a new non-dimensional parameter. We call it reliability index. So that's the transition from the deterministic design to the reliability-based design, because here we have everything is defined in terms of reliability index. Now, I have discussed in detail how this topic has developed. So different researchers, they propose different way to formulate this problem, but by and large, we use the concept proposed by Cornell, and then it was further modified by Haushofer and Lind. So the fundamental concept of reliability index was formulated by Haushofer Lind, and for that, he transformed the reliability index first into standard normal space. But again, the entire theory was originating from the definition initially proposed by Cornell. Now, when you convert the entire limit state equation into the standard normal space, obviously, the reliability based design is effectively a optimization problem. And that optimization problem we solve in the standard normal space. And for that, we need to convert the random variables. And obviously, the moment we transform the limit state in the standard normal space, then we adapt different assumptions. We actually use linearization of the limit state, and that's how we end up with the first order reliability index. Obviously, in this formulation, we started our discussion with mean value first order second moment method, and gradually we developed first order reliability methods. And then also we developed a Rackwitz and Fissler algorithm. That's a solution technique to find out the optimal distance in the standard normal space, because that represents the point which is the design point, and that's the most probable point of failure. Now, during the course, I told you many times, but that because it is a optimization problem, we can adapt any other optimization technique. There is absolutely no restriction. The only thing is Haushofer and Lin defined what is the reliability index, but the optimization problem we can solve in many ways. But one of the stable method was proposed by Rackwitz and Fissler. Of course, again, as it is true for every other method, in this case also, Rackwitz algorithm and Rackwitz-Fissler framework for reliability index also has some kind of background assumptions. And in this case, because it is gradient based, the fundamental assumption is that the limit state must be at least once differentiable. If not, that also we discussed in our course, that in that case, we can adapt numerical technique, but not always recommended. The reason is fundamentally, if a function is not differentiable, obviously, we cannot adapt the gradient-based algorithm. Not only that, in actual case, actual problem, very often we encounter multiple limit states. So obviously, when we have multiple limit states, there can be multiple optima. And of course, the challenges are more to adapt the Rackwitz-Fissler algorithm. Nevertheless, if we can adapt this Rackwitz-Fissler algorithm, even today, this is the most trusted method, and we can easily adapt this because once we identify the gradient, that information we can use to find out the updated design point. Now, when we do so, again, there are two major hurdles that we need to cross before we solve a complex real-life problem. For that, the main hurdle is we have multi-dimensional random variables. That means we have multiple random variables which are correlated. In that case, we need to first define the PDF. Now, for that, we discussed different options. We call it isoprobabilistic transformation. And then using that, we can again develop the joint distribution, and we can also convert from one space into another space. For example, if you take Natöff transformation, then for every point in X space, we have one point in the Z space. And the transformation is really effective. We can easily adapt this to find out the joint distribution. At the same time, we can simulate the samples from the joint distributions. Likewise, we also discussed Rosenblatt transformation. And then we also relaxed the first assumption that we made in case of first order reliability analysis, that our limit states are linear functions. If we have nonlinear functions, we effectively linearize it in and around MP. And therefore, the moment we linearize the function, we avoid the information related to the curvature. And the moment we try to incorporate the curvature, then we get the second order reliability method. And for that, again, we have two options, Brighton and Bent. Now, obviously, it is a modification of the original gradient-based algorithm. And there we incorporate the curvature and improve the estimates of reliability. Once we do that, next, obviously, the question comes in our mind that the estimate we have from this gradient-based algorithm, whether this estimate is correct or not. And for that, again, we have the first option is the simulation-based reliability. And in this approach, we actually simulate the random environment. In general, the method is very robust because we can simulate any random environment, and if we have a nonlinear function, whether it is differentiable or not differentiable, whether we have multiple limit state function, we can easily adopt a Monte Carlo simulation. The only hurdle again in this case is to simulate the random environment. So if we have a large number of random variables which are correlated, in that case, the first hurdle is to simulate random numbers which are correlated and non-normal. Then once we do that, we can manage multiple limit states, and then thereby also we can estimate the probability of failure. We use the basic theory of probability, and of course we quantify the error in PF estimation, and with the number of the samples that we simulate in this case, and that indicates that for a low failure probability we need large number of samples. Obviously, in many practical cases, if we go for what we call crude Monte Carlo simulation, then we need very high computational cost, and that sometimes is very difficult. For that reason only, we have also discussed this variance reduction technique. One important tool called importance sampling approach that we discussed, and it really helps to use much less number of samples to get the same quality result. And once we do that, our next topic was implicit performance function. And there are multiple options we have discussed how to actually replicate a limit state function. And instead of working on the original limit state function, how we can bypass that with the replica of the limit state function. And in fact, if we have multiple limit states or a single limit state with multiple maxima and minima, those issues also we can handle in this approach. And there are again different versions. We have a moving least square approach where we adaptively replicate the limit state function. And of course, in this metamodel based approach, the basis function, if it is orthogonal, it offers even more advantage, computational advantage, and that's how we get basically stochastic response surface. And for that, we discussed in detail how to model the orthogonal basis and how we actually start from a seed and a weight and gradually develop orthogonal polynomials and then use them to replicate the limit state function. So once we do that, that's more or less this second, third, fourth, and fifth module. They are the heart of this course. There we discuss different modeling tools, how we quantify the uncertainty when we have a design problem where we start with the definition of the limit state. Now, after that, we come to the very important topic. We call it code calibration, because in different codal provisions, we see partial safety factors, and we discussed how these safety factors are arrived at and how can we quantify the optimal safety factors, or sometimes even for an existing code where we stand, so for the reliability of the design is concerned. Then in the last module, I introduced you to different applications, and in fact, we also discussed one technique called subset simulation, and that is really a powerful tool, and it is followed by different applications, and at the end, we talked about the formulation of stochastic N. So this is more or less the course. As we progressed in the course, every time I also referred some of the papers whenever it appeared, and also I shared that with you. So that is more or less the overall view of the course, that what we have covered. Now, before we discuss again some of the problems, let us first take the questions that we get. So So let me first share the question and then. Okay, so there is some issue here at this end. So let me read out the question and then one by one, let me answer the question. So the first question is related to ANSYS MATLAB combination when we use a finite element model and then we try to do the first order reliability method. So the question is, after converting log file to .inp file, should we change the value of different random variables in this INP file? Yes, of course. I mean, that's how you change the parameters of different random variables as you progress in the Brackett-Swizzler algorithm. And in fact, there also we showed you numerical differentiation. So for that, again, you have to, adapt either central difference or similar technique to quantify the gradient. Yes, that's what is done by changing the parameters in the INP file and then again run it to get the response. Now the next question is, to extract the response of the structure, where should we write the mentioned DPDL command? It should be at the end, because if you go through the INP file, you can identify how the model is created in the finite element analysis. You start from the basic coordinates to define the geometry of the model, and then gradually you define material property, then different element, you then mesh it, then other issues of finite element analysis. For example, you define the boundary conditions, you define the load, you either go for modal analysis or transient analysis or any other similar analysis. So once you develop that complete model and analysis, and at the end, once everything is done, then what happens? You have to save that response in a output file so that you can read that and use that information for your reliability analysis. For that, I shared not always you extract deformation. It may be accelerations, it may be strain, it may be stress. All those you can actually extract from finite element analysis in ANSYS or similar package. So for that, you need to tune. So your task is to identify the node numbers and then which output need. For example, if you go for stress analysis, then again, there are different options. If you recall, one of the applications I showed you where composite plates are modeled, and then there we used modified Zihel. So that also you can do. Sometimes we use other failure theories and combine different stress components and arrive at the failure of the structure. So accordingly, you have to extract the result from the finite element analysis. And for that respective command, you have to identify from the APDL log and then use that command. So yes, after the analysis, you just copy paste those commands just to save it in an output file so that you can use that information for your gradient estimation. Now, next question is, in make_inp function mentioned in lecture, variable text has long one line of text. Is it the same copied and pasted text of edited INP file? Yes. You can do it in different ways. Actually, you can have it written in the text file also, and then you can call that text file and then run it. But because it was an introductory course, and then we thought to do it that way so that you can follow it. We just simply copy paste the entire INP file and then have it in a single line. But it is not always recommended, because if you have a complex structure, really long INP file, then in that case you cannot do it. And in fact, there are other ways to manage files, although that has nothing to do with reliability analysis. But for simple problems, this is the simplest way. You can just copy and paste it and then run it. It will give you the result. So that's how it was managed. But again, it is not universal. So the problem you have, accordingly, you have to tune your code. Okay, so the next question is, in HOSRSM MATLAB codes provided in the paper by Gavin and Yao, function HOSRSM calls the limit state function when HOSRSM function itself have limit states as its first input parameter. I did not understand how different limit state functions were being fed to HOSRSM functions. Also, I did not get the state function of HOSRSM function. Again, so far this code is concerned, because this is not our code. We did not write the code. It was from Professor Gavin's page and in his paper also. The idea is just to show you how different mathematical models are implemented. So we recommended you to go through the paper and the codes, which is also available. Otherwise, all the intellectual properties of these codes are reserved to their respective authors and publishers. So for the format of this code is concerned, that reflects the way they thought to translate the problem into a MATLAB code. That is not our code, but anyway, you can, the main idea is you can develop your own code. So if you find a better way to represent the same algorithm, of course you can do it. And in fact, we in our case also did it. We modified this code according to our problem. Whenever we used it, although we do not use the same orthogonal polynomial, we always use in our codes Hermite polynomials. We always prefer to use Hermite polynomial. So the main purpose of this lecture was to introduce you to other people's, how they're thinking the same problem, how they're writing. So I will suggest you just adapt the idea, not the code line by line, and you can modify that code and then write it in your own terms. In fact, that will be really helpful, and that's the main purpose of this lecture. So I will suggest all of you to take it up and then write it in your own format, following your own logic. So in that case, if you need to remove the input parameters, you can do it. We handle the limit state function as you have seen in our ways. So we defined a limit state function, and there was a parameter which actually identifies which limit state function we used, and that also we showed you. So if you can manage that way, fine. Otherwise, you can follow the same code. I hope that answers the question. So the last question that I can see in this list is, some of the more involved algorithms like sequential SRSM, adaptive importance sampling, and reliability based optimal tuning of controller using meta model is difficult to follow. It would be very helpful if you go through or provide codes for those complex algorithms. Yes, for these applications, again, these are some of the applications I shared with you, which were published in different papers. Of course, in those cases, we are also planning to upload some of the codes as far as we can do that. Definitely, the main idea is to share the code. So after this session, again, we are planning to provide some additional information, and there you will also get these codes, some of these codes. Nevertheless, for example, if you take the last point, reliability-based optimal tuning of controller, I will share the details of this paper. In fact, when we'll upload additional materials, you'll also see books and research articles that we used. So this is one of our papers. So I will leave that information with you. And if you go through those details, you can develop the codes also. The only thing is, because this is a research problem that we addressed, it involves, again, first the control theory, then nonlinear systems, Bayes isolators, then sometimes magnetorheological materials. So their modeling and analysis is totally different than what we have in these courses. So that's the reason I didn't go through the details of this modeling and analysis. But because this is very relevant, that's why I thought to show you some of the applications in the last module. And as far as the codes are concerned, as I've already told you, we are going to upload those additional informations, and you will definitely get some of these codes. And I'm sure with those codes, if you can develop the model, for example, a Bayes isolator based design using those codes, that should not be a problem. And in any case, if you have any problem, we are always there to help you. So if you have any further issues, do let us know, then definitely we will help you out. But because this covers, for example, the composite plate analysis I showed you. In fact, in one case, crack modeling was showed. That actually, for that, we have different analysis. We cannot go through the details of those because it involves in crack modeling and their how it propagates. So that is somewhat away from the course content of this reliability-based design. But again, I'm sure if you go through the composite modeling and all those, you can easily solve that problem. In fact, we have already identified different problems from different books and research papers. So altogether, around 40 problems we have identified, and we are going to update that in our repository soon, so that you can also go through all those, different limit states, different complexities that we collected from different books and research papers. I will suggest all of you to go through those problems and solve it at your end, because that will give you confidence. And then with that, I'm sure you'll be able to extend it for other cases. Whenever you take an actual problem, for example, this last one, if you take, say, a controller problem and you have uncertainty, then again, you need to first go through the theories of vibration control. But once your idea of reliability-based design is clear, so you can easily adapt reliability-based model for those applications. But all these theories, you can easily club them together to solve your problem. But in this one course, we cannot bring everything in. That's the reason in the last module I introduced it. Anyway, I will update all those informations in our repository so that you can go through those papers. And then if you follow those papers, their equations step by step, you can easily develop the code. And some of the basic codes for reliability analysis, definitely we are going to provide. So that's the last question. Let me check any other queries are there. So no, as of now, no more question. But again, I leave this floor open. So anybody there, if you have any query, any comment, you can now make it. Are you there, Shishir?
Yes, sir.
Yeah. So do you get the answers or you need further clarification? Please let me know.
No, sir. I got it. I got it, sir.
Okay. Any other comments? Any other suggestions to improve this course?
No, sir. It's fine, sir.
Yeah, you can let me know. I mean, see these comments, what you have made, it's very useful. We can also tune our course further.
Okay, sir.
Do you have any plan to extend this theory for your problem?
Yes, sir. That's my goal, sir.
Yeah. So if you go through those papers, I will share that information. I'll share that.
Okay.
So,
Okay, sir.
and also some basic codes. So if you have any problem, do let us know.
Okay, sir.
Any other comment?
No, sir.
So what kind of problem you are looking at where you'll adopt this theory of reliability?
Sir, more on of time dependent reliability problem, sir. Time
Dependent. Okay. What kind of problem?
yes, of I've not gone through, sir, very much, but I'm of sort of a dynamics problem, sir.
No, why I ask you this question again, time-dependent reliability problem, you can view it from a two different angle. For example,
Okay,
if you have, say, a bridge, okay. So the day you construct the bridge, you go for the reliability-based design, and over the year, as time progresses, then the bridge is exposed to its original operating conditions, right?
yes,
So
sir.
then what you can do, you can take some snapshots in time, and every time, say at the end of 1 year or say 5 years, so you can do the reliability analysis based on the data you collect from the field test. So that is one way to actually solve the time dependent. There is a time dependent reliability, but in this case, you are not considering the time as a parameter in your reliability modeling. Effectively, you are doing reliability analysis, whatever we have done, at different snapshots of time, maybe at the interval of 1 year or 5 year or 10 years. Then that is one way to look at the problem. But there are another problem. For example, if you have a structure and when the earthquake comes, then you design the structure for some anticipated earthquake, and in some cases, it may cross the barrier, it may cross the limit. So in that case, within a very short span of time, within the duration of the earthquake, the stress level or the vibration level or the performance of the structure may cross that limit. Okay. So in this case, you cannot have different snapshots of time and do the reliability analysis. That is not possible. So in that case, again, what you have to do, you have to adopt the random vibration theory. So in that random vibration theory, you have to formulate that first passage problem, and then you have to solve the reliability analysis. So there are, it is a completely different formulation. So because we do not cover random vibration here in this course, we cannot solve that problem as such. The reason is that you need to first identify the governing equation of motion, and then you need to define the random process. We didn't define the random process, the properties of random process, and then you have to quantify again the same the limit functions. In that case, it will be a barrier crossing problem. Whether just the first crossing you quantify as your failure or number of crossings, different ways you can formulate that problem. And again, whether you have a stationary random vibration problem or a non-stationary random vibration problem, then accordingly you have to tune your model to quantify the reliability. So that's more complex analysis. So for the time-dependent reliability is concerned. So accordingly, you have to formulate. But that second part, where within a very short span of time, you need to quantify the reliability as a barrier crossing, that we have not discussed in this course. That you have to go through the random variation theory. So what type of applications you are looking at? Are you there? Yeah, so can you elaborate the applications or the problem you have in hand?
Sir, are you? Hello?
Yeah.
Not particularly, sir. I have not gone through, but I'm planning. I'm planning, sir.
Very good. Okay, you formulate the problem and adapt the theory. Let us see. If you have any problem, do let us know. If you need any help, you can reach us. No problem.
Okay, sir. Okay, sir.
Anybody else? So we'll have exam in this course on 28th, right?
Yes, sir.
So
Yes, sir.
online exam. So for that again, you'll have multiple choice type questions. That is, I should say, one of the limitations when we bring this course in this online framework, because many problems actually you cannot solve on pen and paper. In fact,
Yes, sir.
in most of the problems that we have solved, you need additional computational facility, right? So
Yes,
that
sir.
way, judging this in a pen and paper format is difficult. But again, we have to formulate accordingly. So you'll have mostly multiple choice type. And then the idea is, if you go through the complete theory, because it will cover the complete course. So if you go through the theories, it will not be a difficult task. Okay, so that's how we have to formulate in this online framework.
Yes, sir.
And we have to live with that reality. Nevertheless, in this case, so far the reliability-based design is concerned, you extensively need coding. Okay, so
Yes,
you have
yes.
to develop the skills of coding, and that's the reason actually I shared different other formulations and other codes. For example, that HSRSM code I already explained. I didn't develop that code, neither I actually went through the detailed format how the code was written. Only I use it for teaching purpose, and in some cases we compared the results, how our codes perform. So that was our main objective. So you also have to develop that skill of writing codes, because that's really essential in this course. So once the exam is over, I think within 7 days we have to upload the grades, and that anyway we will do. But the point I wish to make is that you take it further, and that's the main purpose of this course. And online evaluation is not the end of this course. It is actually the starting point. Now your task is to take this idea and solve your problem. And in that course, if you have any issues, of course, we will be always there.
Yes, sir. Sir, can I reach you with sir from email, sir, for if I have any problem in later course?
Yes, yes, of course. You are most welcome. I have my IITG email ID, so
Okay, sir.
you'll get it from my webpage. So
Okay,
definitely use that. It will be always there.
Okay, sir.
So any other question, comments? Otherwise, we can close this session. Any comments you wish to make? Final comments?
No, sir.
Well, let us hope that this course is useful for all of you, particularly those who are in masters. So the moment you apply this, you adapt this theory and take it further and then solve your problem. Meaning of this course. So I hope this course will be useful for all of you. And with that remark and the comment that this is the beginning, not the end of the course. So with that positive note, let me close here, and I'll be always there. All of you can reach me in my official email ID. So we'll try our best to help you out. So thank you very much. Thank you very much for all your support. And again, I leave a comment for all of you to help us with your comments, remarks to improve this course further, so that it is more useful for those students who can learn from their home or who can apply this theory for their problems. Not always classroom is available to all the students or the practicing engineers. That is another side of this course, because they are the main taker of this course. So those who are practicing, if you have also any problem, just feel free to reach us so that we can help you out. So with that, let us close here. Thank you very much for all your support throughout the course, and I hope this collaboration will continue.
Okay, sir.
All the best.
Okay, sir. Thank you, sir.